Hey guys, welcome back. This is going to be a redone video on function transformations. It'll be kind of long, but if you stick through to the end, I think you'll have a much better idea or understanding of what is going on with transformations and how to identify them. So right here we see our three most basic type that we deal with in algebra. And the first one is translations. So in this video, I'm going to use the word shift to represent a translation because the translation sounds too much like a transformation. As it turns out, all three of these are types of transformations. So I'm going to use the word shift instead of translate, but the official word is translate. And a translation is just a movement up or down, right or left of the graph without actually rotating it, stretching it to get it bigger, or compressing it smaller, or flipping it over. Okay, so translations are the most easiest of the three types that we're looking here to deal with. But I am going to show all of them. The next one is dilations. And dilations are where our graphs are getting bigger or smaller. And in terms of our straight lines anyway, we're talking about like the slope characteristic or the slope property sort of getting steeper or flatter. So there's two basic types that are broken down into two other basic types. And the first type is you got vertical and you've got horizontal. And each of these has two different types as well. But they're the same two types, just depending on which direction it is. It's vertical or horizontal. And the two types are stretch and compress. And another word that I've seen for this compress is shrink. The graph is getting smaller. So horizontal down here has the same two characteristics, only it's done side to side instead of up and down. Vertical is up and down on the Y and horizontal is left and right on the X. When we get down here to reflections, okay, reflections have a vertical and a horizontal property as well. So vertical, horizontal. And it goes a little bit further than that. So over vertical, we have a reflection over the X axis and horizontal over the Y axis. And I'm going to demonstrate that real quick, how you know which one's which, because the most common mistake made by students is not recognizing whether they have vertical or horizontal, but it's recognizing which axis it's going to be reflected over. Okay, reflection, again, remember, it's like a mirror image, only reversed. Let's say we have the letter R, looks like this, and I want to reflect it vertically. Vertically, that's up or down. So I'm going to draw a line underneath it, and then I'm going to reflect this thing vertically, the best that I can by drawing this upside down. And that would be a vertical reflection. And you'll notice that this line right here that we reflected across is the x-axis. So if you can remember what a vertical reflection would look like, you can always remember that it actually reflects across the x-axis, which is what's shown over here on the side. If we take that same R and we want to reflect it horizontally, that means left and right, that would look something like that. And you can see from left to right that what we have here is this line, this vertical line, is actually the y-axis. And that's how you can remember which way you're reflecting vertically or horizontally, which line are we actually using to cross. So the next thing I want to go over before I show you how these work on a graph is the syntax. And I'm going to use a non-linear function, even though we're basing these on linear functions. This could apply to any function that we can graph in algebra. But I'm going to use an absolute value because seeing a non-linear function happen is more obvious what's going on. So for syntax, right now, wherever I have f of x, it's going to represent this function, this parent function. So this is the most basic of all absolute value family of functions. So the most common thing that we start off with is describing a transformation or a shift like this, f of x plus k. So if I showed you what that looked like over here, that would be the absolute value of x plus k, and it would appear on the outside of the function. Well, this k here, this is just a parameter. So somewhere else we could say that let k equal 4, then this would be f of x plus 4, and the actual function itself would be absolute value of x plus 4. So that parameter there is just waiting for some input value, some meaning. We could also put f of x plus k on the inside like this, and over here that would be absolute value of x plus k on the inside. So we're using the same parameter, only we're using inside directly on x. Now the confusion, I think, comes in when we add multiple parameters. So if I had f of x plus h plus k, then I don't want to have the same variable or the same information in both places, so I can't use the same letters, so I just have to switch up the letters a little bit. So that would be absolute value of x plus h plus k. Now what if I put a k on the outside of my function like this? Then that would be k times whatever is inside the absolute value. What if I rewrote it as a times f of x? Well, that would just be a times the absolute value of x. And if I did a times f of x minus h, and I put a plus k, well, that would just be a times the absolute value of x minus h plus k. And remember, all these parameters, the a, h, and k, all they're doing is they're placeholders. They're waiting for some kind of number or value to come into the problem. Okay, so now it's time to get to the graphing. And this is my parent function. So remember, this is f of x equals the absolute value of x. However, on the picture on the screen here, all I'm going to do is define this as f of x. And the first thing I'm going to go through is translations. Okay, translate. But remember, the word I'm going to use here is shift. So I'm going to use the word shift to describe what I'm about to do. Now, translations or shifts can occur vertically or horizontally. It all depends on where you write your add or your subtract. And that's probably another important information I should have told you is shifts occur through additions and subtractions. So if I said, show me this shift or this translation, f of x plus 3. Well, all this is doing is adding 3 to all of my y values. So if I go to every point and I move this up 1, 2, 3, and I move this up 1, 2, 3, and I move this up 3, and this one goes up 3. These all are going up 3. Then my graph will look like this. So this is f of x plus 3. And I put some points in there, and the reason I did that is this point that was over here, this point, as you can see, was, let me erase part of that. This was 6, 6, but now if you look at the point up here, you'll see that it's actually at 6, 9. So all we did was take 3 and add it to the y column. And that's what we get on our new picture. Okay, so I'll go ahead and do this again, only I will do it with a horizontal shift. So there's our parent function. Let's say I ask to graph f of x plus 4. Now the one thing you want to remember about these is horizontal occurs inside and vertical occurs outside, but horizontal is really the special one. It's always opposite. So instead of adding 4 to our x values, we're going to subtract 4 from every x value. So that means the graph is actually going to shift to the left. So every point's going to move 1, 2, 3, 4 to the left. So that dot moves to the left. 1, 2, 3, 4. 1, 2, 3, 4. And then I can go and draw my new graph, which would look like this. And this is my f of x plus 4. The whole graph has just shifted sideways like that. Now we can combine the two of them together. Okay, so now we're back to my parent function up here. Now let's suppose I wanted to move this thing to the right 5 units and down 3 units. So I do f of x to the right is going to be opposite, so minus 5. And then down is going to be minus 3. So to the right 5 and down 3. Go to red here. So this dot is going to move to the right 5 and down 3, so it moves right here. So it moves to the right and down. This dot is going to move to the right 5, which would be here, and then down 1, 2, and 3. And to the right, 1, 2, 3, 4, 5, and then down 1, 2, 3. And the same thing is going to happen here. To the right, 5 would be at 11, and then down 3 would put me at 3. And I'm going to do the same thing with this one over here. So let me get rid of these lines. Those lines are gone. Okay, so this one's going to move to the right, 1, 2, 3, 4, 5, but it's also going to move down, 1, 2, 3. So get rid of all these auxiliary lines. I don't need them anymore. And then my new graph would be just like this. So I shifted to the right 5 and down 3. So translations are the easiest of those to work on, with the exception of maybe reflections. Okay, so the next one we're going to do dilation. So I still have my f of x here. So dilations. And dilations are types of stretches or compresses or shrinks, if you want to call them that. And then we have vertical and horizontal effects as well. Okay, so let's try some, and I'll explain a little bit more as I go. So this is f of x. Let's suppose I do 2 times f of x. Remember, f of x is the y value. So what that means is I'm taking all the y values coming out of my function. So these numbers here, all these y values, and we're going to times them by 2. So the new ordered pair here, 6, 6 will be 6, 12. This dot moves up to here, and we didn't actually translate it up. We didn't shift it up. We multiplied the y value by 2. So this one will go up to an 8, and this one will go to a 4. And 0 times 2 is still 0, so this dot actually stays put. This one will just move up to here. This next one will move up to an 8, and this one will move up to a 12. And when I go to graph this transformation, what you can see is, number one, I did a vertical, so vertical, and the graph got steeper. We call that a stretch, so that's a vertical stretch. What you want to notice is the number that I used inside here was actually bigger than 1. And anytime you multiply by a factor bigger than 1, you're always going to get a more narrow look to the graph, whether you multiply inside by that number with the x or outside with the y. The effect looks similar in either case. All right, so let's do the same thing, only I'm going to leave that graph there, but I'm going to put a 1/2 on here instead of times 2. So over here, that was called a vertical stretch. Over here, I'm going to put a 1/2 on the outside of my function. So I'm going to take all my y values and divide them by 2, or multiply by half. So this y coordinate becomes a 3, so it goes down to right here. This one becomes a 2, so it goes down to here. This one becomes a 1, so this one changes to 1. Again, 0 times 1/2 is still 0, so this dot's still there. Right here, and you'll see that the graph goes a little bit wider. It flattens out, it compresses vertically. So this is outside, so this is still vertical. So you can call it a vertical compress, or you can call it a vertical shrink. What causes it to be vertical is your multiplier, your 1/2, is outside of the function. It's happening directly on the y values. So anytime you multiply by a fractional value between 0 and 1, whether you multiply it inside or you multiply it outside, you'll get a widening or a flattening of the graph. Okay, let's change it up a little bit. Let's go back and do a times 2, but we're going to times the 2 on the inside with x. So 2 times, or f of 2x. So remember, that would look like this, absolute value of 2 times x. Now, remember what we did before when we did translations, which were shifts. Everything was opposite. So when we see the 2 inside like this, my x values are not going to get 2 times as big. They're going to get half as big. So the multiplier that comes out of this is always the reciprocal. So it's going to sound, the picture's going to look weird, but even though when we multiply by a 2 here, we're going to get the same effect as multiplying by 2 on the outside. But what we're really multiplying by is not 2, but by 1/2. So the x value that's here on the 6 becomes half as big. So my new ordered pair, instead of having 6, 6, I will now have 3, 6 for the new point. So that point will move in 1, 2, it'll actually move in 3 units right about here. So 1, 2, 3 units over, it gets half as big. Same thing is going to happen to this one, so that's going to become a 2, so it's going to move over to here. This one's going to become, or this one's going to become a 1, so it moves over to here. Now, dividing by 2 or times by half on the 0, this dot stays in place. I'll get rid of those lines. And this one was horizontal because it happened inside the function. So this one's horizontal. But this one's not called a stretch. This one's called a compress or a shrinking. And the reason for that is, remember, this effect is horizontal, which means on the dotted line here, we're pushing in from the sides. And when we push in from the sides, the effect is the graph moves closer together towards center, which is what happens when you take half those x values, and it creates a more narrowing effect of the graph. But we don't call it a stretch because we're pushing in from the side. We call that a compress when we push things together. Well, a stretch is when we pull them apart. So what would happen if I put a 1/2 on the inside? So f of 1/2 x. Well, instead of taking our x values and multiplying by half, we're going to multiply by the reciprocal again, which would be 2. So going back to this point right here, we're going to take the 6, and the x value here, we're going to times it by that factor of 2, and that will give us 12/6 as our new point. So I got to move this out of the way. So that point moves all the way out to 12/6, which is way over here. And the same thing here, I times the x coordinate by 2, and it moves this dot all the way out to 8. So 4 times 2 is 8, 8, 4. And then I multiply this one by 2, and that moves me out to 4, which is right here. Get rid of those lines. Don't need that anymore. Now, when I multiply this 0 by 2, I still get 0. And you'll notice the graph got wider when I multiply by half. That's because we are making all the x values go 2 times further out. Now remember, this was 1/2 x, and then inside the function. Now, because it happened inside, we call it horizontal. And because we're actually pulling the original lines outwards, we're pulling them left and right, that would not be a compress anymore. That would be a stretch. So this is a horizontal stretch by a factor of 2. Okay, for our last transformation, we still have f of x, but now we're going to talk about reflection. Now remember, reflection, where we had the r, we have a couple types. So we have r like this. I can reflect it vertically, which would look something like this, which means I'm reflecting across the x-axis here. Or if I want to reflect it horizontally, let's say I have an r here and I want to reflect it to the left, then that would just be around this way, and it would look kind of like that. And this would be the y-axis, whereas the other one was the x-axis. So vertical reflection on this side and a horizontal reflection on this side. So identifying if you're talking about a vertical or horizontal reflection, again, is a matter of where does it happen? Does it happen inside or does it happen outside? So if I have negative f of x, this is happening outside of the function, so this would be a vertical reflection. Now on the equation itself, this would look like negative absolute value of x, meaning all the y values coming out of the problem will end up being negative. So this is going to reflect vertically, which means it's going to reflect across the horizontal line, which is the x-axis. So yes, it's controlling the y up and down, but it's going to flip over the x-axis. So putting a negative on the outside like you see here, all that says is go to every one of your y values here and make them negative. So this point over here would be 6, -6 instead of 6, 6. So if I go to 6, -6, you can see that I have a dot right here. Same thing for the 4. 4, -4 would be here. And then the 2, -2, or the 2, 2 will become 2, -2. Now multiplying the 0 times the negative isn't going to change, so this vertex here actually stays the same. And then we apply the times negative to all of these y coordinates over here again, and we end up with, so the graph just flips vertically upside down, just like this. And that's what a vertical reflection looks like. Now, while we're on this topic, I do want to show you how to combine multiple transformations before I show you the horizontal reflection, because I have the graph up here. So up here we had negative f of x. What if we said to do negative 2 times f of x? So we actually have two transformations taking place. The first one is the reflection, and the second one is a vertical stretch. So I can reflect my graph and then take all these points that are here and then stretch them by a factor of 2, which means they're going to get 2 times steeper. So this one will move up to a -4. This was at a 4, so it'll move down to -8. And this one was a 6, -6, which will move to a -12, which is actually off my graph, but I'll put a dot there anyway. So get rid of those lines. And the same thing is going to happen over here on the left-hand side. So my new graph, and of course, 2 times 0 is 0, so my graph actually ends up looking like this. So you can actually combine multiple transformations. You don't have to just do one at a time. But when you look, what's important is when you look at this right here, the -2, you shouldn't see it as a -2. You should see it as a negative and a 2, which is 2 different transformations. Okay, for horizontal reflection, I had to move my graph off center, and some of you probably already realized why I had to do that. Because our axis of symmetry is the y-axis, and we are always, when we do reflections, we're always horizontally reflecting across y. Since the axis of symmetry and the reflection line are the same line, you wouldn't see anything change. For example, if I drew the original graph back in like this, and I were to reflect it across the y-axis itself, the graph would land back up on top of itself and you would not see any change. So I intentionally moved this off center, and I'll go ahead and explain how I did that. If you look over here at the vertex, this was at 0, 0, which means I had a horizontal shift of 4 to the right, so that would have been f of x minus 4, and that caused the dot that was here to go 1, 2, 3, 4 units to the right. So a little review of translations there. Okay, so I had to move that over. So let's do a horizontal reflection. Now, horizontal means it has to happen inside, f of, and then inside it, to make a reflection, you're just adding a negative to whatever's in there, so a negative x. And this is going to be a horizontal reflection. Again, as we said before, this negative inside, all it's doing is adding a negative to each of your x values, including this one down here now because it's no longer 0. So adding a negative to each one of those values. So let's go back to the first point. If I add a negative to this 10, that becomes negative 10, 6. So if I plot that point, negative 10, 6 is actually over here. So this point moves to the other side. And if I count this out, I'll show you why that works. If I count this out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, until I hit the vertical line. And then I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it stops. And that's how the reflections are going to work. Okay, so I'm going to reflect this one by making it a -8. So -8, 4 would be right here. And this one right here would be -6, 2. So -6 and 2 would be right here. And then if I reflect this one across the y-axis, that would just give me a -4, 0. Now to do the other points, I'm going to do them in gray. So I'm going to change the -2 here to a +2, 6. So +2, 6 would be right here, +2, 6. And change this one from 0, 4. So I'm just changing it to a negative, so it doesn't really change, it stays put. This one, I put a negative on there, so 2 times negative is -2, 2. So -2, 2 would be right here. Let me get rid of these lines or these other dots. And now you can clearly see that the line or the shape is going to go this way and this way. And it is a horizontal reflection of that graph.